Okay, we thus conclude the chapter on the Möbius function, which I hope that you've been enjoying so far. If not, you can just drop me a mail and say anything that I need to improve, or any topics you want me to talk about. I really don't mind sharing about them. Okay, so the Möbius function, something that we see. Okay, what's its applications? They've got the Merton's function. Other than simply finding a number to disprove the Merton's conjecture, which is the Merton's function divided by x to the power of half, the modulus is less than 1. Okay, sorry, yeah, it's less than 1 to disprove that. Okay, however, from the Möbius function comes 4 powerhouse identities, and man, I did try to look in the proof of some of these and I couldn't find any, but for mathematicians to work day and night finding these identities on such an erratic function as the Möbius function, and to find out these identities, man, something great is going on. Now, I don't know who found them, okay, but I will look more into it and I'll let you know. Okay, there are 4 powerhouse identities that uses or involves the Möbius function. Okay, the first one is the summation of n equals to 1 to infinity of the Möbius function divided by n is equals to 0. Okay, I mean, something like that already amazes me. So you apply the Möbius function, okay, you divide it by n, the integer which you use to apply the Möbius function, okay, and you sum it up to infinity, you will get 0. Okay, the second one, summation of n equals to 1 to infinity. However, it's a bit of the same thing. Okay, you take the Möbius function of n, now you times by ln n, okay, and then you will divide it by n, you will get minus 1. Rather similar, just inserting the ln n. Though I must say, when you insert ln n, things changes a lot, okay? But that's how the function goes. Okay, and the other one is the summation, okay, of n equals to 1 to infinity, and this time we will take the modulus of the Möbius function divided by n squared, and we would get, interestingly enough, 15 divided by pi squared. Okay, now if you can remember my earlier talk about head 0, this 15 and pi squared, the pi squared comes in 6 divided by pi squared. That's the probability of picking a number that lands up in head 0, okay? So that is the third identity. And the last one, which I would like to really call the grand identity, and my goodness man, okay, is the product sequence, or the product sequence of n equals to 1 to infinity of 1 take away x to the power of n to the power of the Möbius function n divided by n, just like how we applied the summation of the Möbius function divided by n. But this time we're taking this thing to the power of that, and that is equals to transcendental number e to the power of minus x, where the modulus of x is less than 1. Okay? Wow, that one really needs a lot of work. I do not know whether it's in the realm of like a 50-page proof, but I would really love to know, okay? And really want to go to a place where I can study this, a good place. Okay, so anyways, is the product of this sequence, the product sequence of this thing over here to infinity. Okay, bearing in mind that something interesting is that this one, we can insert the variable x. You see, we've got a variable x here that we can actually insert over here. So what I did was that it goes something like, okay, the x, let's just say is 0.5, 0.5 is less than 1, so we got 0.5 to the power of n, okay, and then if it's n is 1, it'll be 0.5, so the first one is 0.5, okay, let's just focus on this one over here. So the first one is 0.5, the second one will be 0.5 squared, so 0.5 there will be 0.25, and that will be 0.75. Okay, so on and so forth. Now it's 0.5 times 3, I think it's 185. So it'll be 185, 185, that'll be 185, 115, I think. Okay, doesn't matter, something like that. Okay, now the reason why I left gaps over there, because firstly the product sum, and secondly, we're not multiplying this number together. We are taking these numbers to the power of the Möbius function divided by n. So the Möbius function is now involved as the indices, and I find that very interesting indeed. Okay, product sum to infinity, product sequence to infinity. Okay, and those are the 3 identities. And given my limited and humble understanding of mathematics, I can perhaps talk about this one over here. Okay, these 3, leave it to when I got a master's, I'll talk about it. Okay, so I mean I can just talk briefly about this first one. Okay, And what does it seem? Okay, it's the sum. So that's quite easy enough to understand. And we know that the Möbius function, we only got 3 values, correct? -1, 0, and +1, the 3 heads. Okay? And we're taking the sum. So notice that n is at the bottom, and n increases and the positive integers increases. So n would really go on and go on and go on. Okay? So what I can kind of suspect though is that because of the Möbius function, we will cancel out, the certain values, and that's why it converges to 0. So if I could just recall the Möbius function, okay, -1, 1, 0, -1. Okay, so it's 1, -1, -1, 0, and then I think it's -1, 1. Okay, so it's -1, 1, -1, 0. Okay, this is the Möbius function n. Okay. So this thing is saying that we are taking these numbers over here, but we are dividing it by the integers that we used to apply the function to. So there will be 1 minus 1 divided by 2 minus 1 divided by 3 plus 0 minus 1 divided by 4 plus 1 divided by 5, okay, and minus 1 divided by 6 plus 0. Okay, is that correct? 1, 2, 3, 4, 5, 6. Sorry, okay, minus, so it's plus. Sorry, 4, so 5 is here. My apologies, 5 is here, 6 is here, 7 is here. Okay, and when we take the sum of this, it will equals to 0. Okay, now, if you will look into my calculus section, okay, there is a sum function that is quite similar, not exactly the same, okay, but I would really, that was the comparison that I drew, and that was how Leibniz calculate pi divided by 4, okay, which is 1 divided minus, okay, now I need to recall it, I think it's 1, oh yeah, okay, sorry, 1 plus is 1, 5, I think it's 3, yeah, 3, 5, 7, correct, okay, 3, 5, 7, 1 plus 9, I hope that is correct, 1 minus or plus, doesn't matter, okay, so really,